You are on the screen.
Good evening from Assam, India. Earlier this morning, we witnessed a lucid and articulate lecture from Professor M. Al Hussein from Bangladesh University of Engineering and Technology. I make it a point to recurrently inform all the participants that all the lectures of this workshop are streamed live via the official channel of our institute, that is CSIR SRTP, and therefore recorded session may be viewed anytime from there. After each lecture, the YouTube link of the respective lecture is shared in the WhatsApp and Telegram group. Even as 3 lectures are yet to be delivered, we have been great diversity covering almost all the subdomains of seismology and tectonics. We had talks on classical seismology, engineering seismology, seismic hazard, seismic precursors, strong motion, future insight, and elucidation of tectonics and seismotectonics of several complex regions of the world. Yes, we are mesmerized on learning about a strike-slip fault on continental crust causing a tsunami in the Southeast Asian tectonics. You have the opportunity to win Rabindranath Tagore Prize, nominated by Professor Walter Mooney, if you have scientific explanation to it. Coming back to the second lecture of the day, it will be presented by Professor Sebastiano DAmico from University of Malta, who is going to give a talk on the salience of computing seismic hazard maps and incorporating site effects. In this session, we have with us Professor J.R. Kyle, former Deputy Director General of GSI, Government of India, as a session chairperson, Dr. Saurabh Barua, Chief Scientist of CSI NES Jurat, as a session co-chairperson, Dr. Ayodeji from AO University, Nigeria, as a guest. So before the session begins, may I now request our session chairperson, Professor J.R. Kyle, for his remarks. Over to Professor J.R. Kyle.
Thank you so much. Hearty welcome to Professor Sebastiano. We just met a few months back in the month of February. We first met in University. Both of us at the Geology Department, Dibrugarh University. Then we both attended the Infrahat. And it is so nice to see you, Sebastiano. Professor Sebastiano, it's so nice to see you. It has been nicely organized by your good Dr. Santanu Barua. And because he is dynamism, we are listening to many good lectures, excellent lectures, and we are also lucky to see you again among us, and we look forward to your excellent lecture on the earthquakes in Italian seismic hazards. Thank you so much. Welcome to our international workshop. Thank you so much. Over to Shantanu.
Thank you very much, sir. Now may I request our co-session chairperson, Dr. Saurabh Barua, for his initial remarks. Over to Dr. Saurabh Barua.
Good evening, everyone. Good morning from India as well. Honorable Professor J.R. Kayal, today's guest of honor, eminent personnel lecturer, Professor Sebastiano from Malta, Dr. Shantanu Barua, the convener of the particular international workshop, and Mr. Dr. Ayodeji Eluemi from Nigeria, my dear participants. If we remember the lecture delivered by Professor Susan Howe, where she mentioned it's really a challenging and daunting task to develop a seismic hazard assessment map, seismic hazard map. The very reason she mentioned that the GMPE, that means ground motion prediction equation that we develop region-wise, that it has to be really a optimal one. And to obtain a ground motion prediction relation is really a challenging one. And as we have a very good empirical relation, we can think of a good seismic hazard map. So over the last 3 lectures by Professor Susan Howe, Professor Hussaini, we have seen what is the requirement for seismic hazard assessment. And today, Professor Sebastiano is with us, and he will deliver another important specs of seismic hazard assessment map. And he is an expert. He has contributed immensely on this aspect globally, and he is really a global scientist who has contributed a lot in different countries. And recently, few months back, he visited India as well. And we are eagerly waiting to hear from him. Just I'd like to say, on behalf of Northeast Institute of Science and Technology, we really thank you for accepting our invitation to be a part of this international workshop. Thank you so much. I hand over the platform to Dr. Shantanu.
Thank you very much, sir, for your initial remarks. Now, may I read the short biodata of Professor Sebastiano DAmico. Sebastiano DAmico has been working at the University of Malta with the Department of Physics and Geoscience since 2010. He was enrolled in the physics program of the University of Messina, where he was awarded the title of Dottore in Physica and holds a PhD in geophysics from University of Naples. In 2005, he moved to Rome, where he joined the INGV. In 2007, he married Rosa Riana, and together with his wife, he moved to USA to join the St. Louis University till 2010. His research interests are in applied aspects of geophysics and earthquake seismology. In particular, he is interested in seismicity and tectonics of the central Mediterranean, earthquake ground motion, and seismic hazard, earthquake moment tensor solutions, and ambient noise measurement on soil and buildings. In the last year, he carries also research at cultural heritage and archaeological sites and uses modern technologies such as virtual reality and image processing, as well as geophysical techniques to reconstruct buried structure and or past status of the artifacts. He is the author of about 100 peer-reviewed publications. He was also the former Vice President of European Seismological Commission. So with these few words, may I request our guest, Professor Sebastiano DAmico, for his deliberation. Over to Professor Sebastiano DAmico. Thank you.
Thank you, Santano. I shall share my screen. And can you tell me if you can see the screen, please?
Yes, we can see.
Yeah.
Okay, fantastic. Just one sec. Very good. Okay, thanks for the invitation to join this meeting today and this nice event you organized. Just one, okay, can you still see it, right? Very good. And today I'm going to speak about the challenge of computing seismic hazard map and also incorporating side effects. This is a quite important issue for us, being a small island in the center of the Mediterranean And therefore, I'm going to cover some of the aspects related to this challenging. I will not go into the issue of ground motion prediction equation as it was earlier mentioned, because we had a lecture already on this, but indeed it's another important factor that we need to tackle and keep it in mind if we want to compute realizable hazard maps. So as an overview, why we're doing this? Because obviously we want to make awareness of the seismic history of the Maltese Islands. Also, it's necessary because there's a rapid increase of building density and building heights. It's an island, we don't have enough space, so people are building and always taller and taller buildings. So this is extremely important. Thus, the side effects can be an important value and related to the local geologies as well. But just in the few recent years, we started to actually gain knowledge on those aspects. And of course, we need also to include this into the legislation in order to enforce the results of the research. So I would like to start with a statement that earthquakes don't kill. And actually, we do have, we should learn, and we do have several timelines. So we do have an emergency phase that actually the duration has reduced for a few seconds and minutes. It's where everything happens. Then we do have months to recover. And then what I call it preparation phase, it's something that will take decades, sometimes centuries, in order to have the next big one. It's when we need to be ready with our stuff, with our studies, with our research, in order to improve the knowledge and strength as much as we can our environment, built environment, of course. Before we go ahead, just as a little reminder, I hope you allow me to give this definition and clarification about the difference between risk and hazard. They are not exactly the same, but they are connected. Risk can be considered as the convolution of hazard, vulnerability, and exposure. So it's a complex factor that takes into account also the building stocks, their value, and therefore there's a high society implication in this. The hazard instead takes into account the physical phenomenon that we're looking at, and we are going to try to give a certain probability of a certain value to be in the exceedance side. Thus, in order to clarify a little bit further the difference between hazard and risk, if we consider that this is going to be an hazard map, so it's going to be our goal eventually, then hazard doesn't necessarily coincide with risk. If we take Canada as an example, and assuming that this seismic hazard map represents the reality, we know that the population, for example, and the 4 major cities, all the major infrastructure are located along the US border, okay? So the risk, it will be higher in some part of here and here, where all the majority of the population resides, where we don't have the largest infrastructures, but it will be very low right in the north. Despite the fact that still we don't have hazard. So hazard is related to the physical phenomenon. Risk is a little bit more complicated, and it takes into account society element as well. Let's jump into the clue in the focus of this talk. We are in the central Mediterranean. This is Sicily, southern Italy, and we're located in Malta. As you can see, this is a very tiny island, sorry, in a quite seismic tectonic complex region. And the challenge of computing seismic hazard in here is because we don't have, at least we didn't have, so complete catalog still a few years ago on which we can base our interpretation. And also lack of study related to side effects or regional calibrated ground motion prediction equations. Those are few of the challenges that we're facing and that we're working on in order to solve this problem and to have an accurate, as much as possible, seismic hazard estimate. Indeed, seismicity, it's an important, and background seismicity is an important factor in the computation of these things. And as you can see, this is a simple map in which we do have color-coded the earthquake that we record at our own network now, and in red. In blue, instead, we are like the official bulletins, in this particular case, given by INGV. As you can see, the smaller events are not properly detected, just because we are off of the Italian region, and there is not enough coverage, being a large portion of sea. So the small earthquakes are not always detectable. So it's really important actually to try to detect those in order to get information on potential seismogenic structures. The other challenge is that the lack of events, the lack of station, also results in a lack of the computation of the moment tensor that actually can give information on the local geodynamics, can give information on the seismotectonic of the area, and therefore constrain as much as we can eventually our hazard studies. So our problem is the monitoring, and eventually even real-time monitoring. And we went up to 5 or 6 years ago, before actually I came here, there was just one single station located in Malta. So it was implemented a single station location method to actually appreciate and try to locate as many earthquakes as possible that were not detected by the network, which was far away of 150 or so kilometers at least. Now we went to a network location, and I will show you some about it. Now, the small events obviously are not recorded very well. They also suffer by poor constraint, and all the stations in a case similar to this are located to the north. And also there is real-time problem connectivity with the few stations that are located in northern part of Africa. So, see if it goes on. Oops, sorry. Sorry, my bad. So the philosophy behind the single station location is that eventually, even from just one recording, we can get information on distance and back azimuth. So even though we don't have the any information on the depth of the event or any other potential other information that are useful, at least from this we can get an indication where the earthquake has been located. And we had the automatic epicenter location in place that works daily. And through some processing that you can find all the details in this SRL paper by Ajus and Gallia 2011, sorry, you can see how the system was designed to work on real time. And that's how the majority till 2012, 2013 of earthquakes in red have been located by using just a single station method. So having an information on potential seismogenic sources, but with no information on the depth. Now we moved to a more dense seismic network. Just to give you an idea, the island is about 300 kilometers square, and we do have 8 new permanent stations. All of them are broadband, and the network has been fully registered, and the black one instead are the planned stations that are going to be in place in the next few months. So it's a quite dense array that we have now on the island. This is the historical station that we had that has a Strackhausen sensor, while all the new stations are equipped with more modern technology and state-of-the-art instrument. All these stations are feeding in also in a real-time system. We use basically SeisComp to time location and give alerts. And everything is fed into our website, in which we report in quasi-real time all the events in the region. The IT infrastructure also takes care for the network of the virtual network, because we don't have just our own stations, but also we take advantage of the sharing data with neighbors countries such as Tunisia, Greece, Italy, and we do feed our system like that. Recently also we incorporating sea level stations, and the Tsunami Simulator TOST is running in order to give potential alerts for tsunamis. And this is still a work in progress. Obviously, all the data are archived, on request are available, and for any different studies, not just related to earthquake location, of course, and everything is also offline backup for being used at any time. The activity also we lies also with the civil protection, so we send regularly as long as there is an earthquake in our region or nearby, an alert and a report to the civil protection authority, so they at least are aware and informed on the activities that actually is taking place nearby the island. We do have a system also which is called Did You Feel It? It's very similar to several others that are available in several countries and even globally. But we need our own, because in case of small earthquakes, this is a small event that occurred about 10 years ago now. Actually, it was recorded at that time by just one station on the island, and this is the questionnaire response to the earthquake. And very few have been submitted on the global, just because the local people, they submit questionnaire to the local authorities. So it's important to have a local system in place. So as you can see, we had quite a number of responses, and of course this was a nice exercise to actually try and test the functionality of the system. The other challenge we said we have, besides the earthquake location that now we can rely on more stations thanks to the network, is the challenge of computing stable moment tensor solution as well. So in order to do that, what we actually do and have in place, it's based on the cut and paste method. This is an offline, so it's not, it's working in real time, but obviously it needs a lot of tweaking by the analyst and verification. But basically, it's based on a general velocity model. The green function is pre-compiled, and after a certain process, we are able to fit and to compare real data and observed data. So to compare our greens function with the real data, and able to get moment magnitude, additional information on the depth, and also information on the source mechanism. That's how the processing will look like. And in general, the beauty of this system, it's perfect for a place like ours in which we don't have a large back-azimuth coverage. And this system, instead of inverting the full waveform, will invert separately the P arrival and the surface wave arrival, weighting a little bit more the wave arrival, as you can see in here from the amplitude of the phases, and eventually get a fit with the synthetics and observed data. And thus, through a grid search method, able to identify the focal mechanism parameter, the depth, as well as the moment magnitude. This I will skip. So this is one example on which we don't have little azimuth coverage, but in which the method is quite successful. This is some other examples of waveform fit for some for the events that we just saw. Thus, we are able to compile and have information on the seismotectonic of the area, and thus infer or confirm what other studies have done related to the local seismotectonic setting and geodynamic conditions. Let's see now to put this all together, and let's try to have an overview on this. I would say that there is enough seismicity all around, so we don't have catalogs, we don't have information on historical seismicity, even large magnitude events. In here we are representing just the one with 4 and above. And everything also it's in view of the historical seismicity. Those are the time histories for two islands, Lampedusa, which is an Italian island, which is located just west of Malta, and Malta. As you can see, they experienced in the past several earthquakes, and some of them have been quite, like the 1693 and the 1908, quite important for Malta. Consider that at the time of the 1693 event, around 20,000 people lived on the island. Today, the population on the island is of about 500,000. So, of course, in this regard, you might foresee what the problem eventually would be in case such an event will strike, and we need to get ready. So in order to compute the seismic hazard for the Maltese Islands, we have to take into account seismogenic sources. So we don't have an hybrid approach, and our logic tree, besides the catalog, it implies that we don't have two branches in our logic tree for the source model. In particular, we don't have one which is based on seismic zonations, which is the one that you see above, and the other one which is based on seismic zonation and fault zones, because we are able to identify also some fault zones also through projects and some European projects that are named F1 to F4, and those are giving a little bit more weight. The other problem and the other challenge is that for the both branches, we need to have obviously our recurrence time, and this has been computed already, but also the right attenuation law. So at the moment, we're using just one normal attenuation law that are available in several papers, but also we are working using neural network. I do have a PhD student, Sharon Patch, that she's working on identifying and to calibrate an attenuation relationship using neural network approach for the region. And this will be the first calibrated attenuation relationship that will help in improving our seismic hazard computation. This is some preliminary results for putting all together and following the approach that we just mentioned in the logic tree. Everything is based on rock, so no geology whatsoever, including this in this plot. And as you can see, even the mean in terms of PGA at several locations, it can reach 0.1 and more G. Of course, it's important to take also into account the spectral acceleration at different periods or at different frequencies, if you like, and do de-aggregation studies. This is important because we might have, and we do see, the contribution of small events at small distance, but also the contribution of large events at large distances. Large events at large distances means that our buildings could be also sensitive to very low frequency or quite high periods. Thus, since we're building nationwide with taller and taller building, that's something that needs to take into account in details. Now, the major challenge, as we were mentioning, is the side effects. Now, there are several approaches, and on this regard, we can see how Italy has implemented already guidelines for seismic microzoning, and then the proposal to a site characterization that actually, for the Maltese Islands, and some examples that actually would serve emergency planning or in general planning in general, take into account the particular geology, because even if the geology is, as we will see, sedimentary, there are some features in some portions of the islands that could be a challenge, and we'll see this in a moment. So in general, what does it mean side effects? Take into account the little final portion of the geology, and as you can see, not just the epicentral distance, but also at large distances, something that is located on soil, on bedrock, this will serve as an amplifier. It will amplify eventually the ground shaking and can cause severe damage. Obviously, we do have several conditions that also taking place. It's not just the local geology or soft layer on top of a rock layer, but we could have also topographic effect, valley effect, or velocity inversions in the stratigraphy. So with the term microzoning, we tend to identify and characterize areas that have different seismostratigraphic morphological features that can influence the seismic hazard. So this is necessary at a local scale for city planning and can be at different levels. Now, this is for the Italian way of dealing with microzoning. They do have 3 levels, level 1, level 2, and level 3, in which level 1 is the simplest, and you can read from here what it's necessary. Basically, it's a kind of speedy way of microzoning a certain area, and there are very light geophysical perspectives. Does this produce geolithological map and maps with microzoning at scale 5, 10,000, 1 to 10,000. Level 2, it increases a little bit the approach. There is a definition of with the 1D seismic response, and besides the ambient noise, there will be also MASV and other active and passive seismic technique to identify the subsoil and subsurface from the geophysical prospecting point of view. So it will be more detailed map, and we do have 1D vertical heterogeneity geomorphological configurations that eventually we can use, and then divided the different zones according to the local hazard, so we can classify them. Then we do have the final and in-depth microzoning map, in which we can do an advanced 1D or 2D numerical model, and of course, the computations of response spectra and stuff like that. Now, I'll give you an example why these things are necessary. This is a small case studies that we had in northern part of Sicily. The name of the place is called Rometta. And as you can see, it's a nice village that is located on top of a hill, completely isolated, and just the top part is not built up. The rest is completely built up, and that part is the ruin of the old castle. So this part, it's a park, and nobody can build. And as you can see, even from historical picture, it has been already built this way. It's a small place in which everything has been taken over. The geolithographic, lithostratigraphic conditions are the one that we can see basically in this picture. But what is interesting is that on top, which is the red part underlined in here, we do have a formation of the clay. Okay, so clay on top of limestones. And in here, we can see that the clay doesn't cover the entire top hill. It's really that way. Now, historically, earthquakes has given several damages in here, but we don't expect this because it should be located on rock, and being the clay confined just on the top part. So the soft soil is confined just here according to the map. So on the right-hand side in here, you see several ambient noise measurements. This is simply H over V. And at between 1 and 10 Hertz, what we can see is the presence of several peaks at different frequency. And each of those are the points of investigation. So not everything it's on rock, on limestone. So there is something going on that we wanted to investigate. In order to calibrate our measurements, we also took some array, and we tried to define seismic velocity profile as a function of depth by combining through the genetic algorithm approach the dispersion curves and H over V data. So as you can see, if we take one profile, the peak is changing, and it's actually moving from 2 Hertz higher values, and then the peak disappears at the point 4. So it means that just on point 4, somewhere here, we are located on the limestone. The rest, even though the geology map, so the first level, will say it's on rock, actually it's not. So what we did was actually reconstruct the geology in this area, and able to demonstrate that it's not just the red part where the clay is present, but it's also in here, and just very few points in here of the village and in here are not located on clay. Okay, and that's where historically here and here no damage have been reported during strong earthquakes. In here instead, a lot of damage. And just as a curiosity, on the steep there is a building that actually survived at several earthquakes for about 800 years. So it's really on rock. VS30 is a good proxy because there is also the tendency to use everything based on VS30. Now, from this point of view, if we jump on the Maltese Islands, we can see that the frequency and the resonance frequency to the geology is not always the same over the Maltese Islands. We don't have any peak on this part, but we don't have peak on this part. This is due, and this is because we don't have in the geostratigraphic section hard limestone, and below it we do have soft material, which is clay, and then we do have again hard limestone. So in our case, we will demonstrate and we will see that the VS30 might not work. Okay, and that's what we see in this part of the island. So we took a bunch of measurements, both in terms of array, then H over V measurements, in order to actually study the effect in dispersion curves and actually get information on the subsurface. As you can see, similar geology will give different VS30 values in the order of 400 and 660 meters per second. So is really VS30 a good proxy in our case? We don't think so. And if we look at this, and all those the results are published, and you can have a look at those papers, at the spectral acceleration as a function of frequency for the site-specific and site class A, B, C, and D, so varying the soil condition, we do have some differences. And in our case, if we look at the PGA amplification factors, as you can see on the western part of the island and the sister island Gozo, which is the small and tiny island of the north over here, we do have amplification factor that needs to be taken into account. And as you can see, also, those are different locations on the island. As you can see, this is the EC8. This spectrum are quite different. They don't follow the EC8 code. So this is something that we need to work on and to keep working on to actually make regional regional curves that can be used for our own case, in which VS30 is not a good proxy. All this information, besides the computation of seismic hazard that we see, besides integrating the seismic hazard and the potential side effects into it, are important even for building scenarios, for example, for civil protection exercises. And this is one scenario for the Maltese Islands, and for PGV, PGA, and different spectral acceleration. For an earthquake that is located about 150 kilometers away in Sicily, and of a magnitude 7.6. As you can see, in this case is predominant the effect of the geology, and you can see both in the PGA and the spectral acceleration that the northern and western part of the island will be affected, and the geology will be giving a contribution. Okay. This is another simulation and another scenario for a lower event. We are around magnitude 5, and we are located about 20 kilometers south of Malta. So we will see that in this particular case, the source is more important than the geology, because we are in the near field. So geology still have and can play a role, but also the source and the earthquake location and vicinity will have a role. So we need to take all this information into account to compute proper seismic hazard maps. Now, in terms of the concluding remarks, that we can say that increase of the permanent stations will help any region in gaining more data. And eventually array technique can be used in order to improve seismic monitoring and locate low magnitude events. This can help in finding more information related to the potential seismogenic sources. And obviously we need to characterize those as best as possible. And then it's really important to evaluate seismic site effect and incorporate them together with microzoning studies in order to have reliable and stable seismic hazard computation, and then move into the risk assessment together with the engineers. Thank you for your attention, and if you have any questions, I will try to reply to them, I hope. Thank you.
Thank you very much, Sebastiano, for your very brilliant talk. You have discussed the potential challenges in determining ground motion parameters, as well as challenges in quantifying the local site effects in seismic hazard analysis. Now, may I request our session chairperson, Professor J.R. Kyle, for his comments. Over to Professor J.R. Kyle.
Thank you, Shantanu. Thank you so much. Yes, hearty congratulations, Professor Sebastiano. You have made a very wonderful presentation and made us, enlightened about the small island with big problems, right from initial instrumentation to geological problems, source problems, and you have also showed us how VS30 is not really working. So many challenges and so many problems in the small island. I think you have given us a very good picture of the seismic hazard challenges. Thank you so much for a very educative lectures. I think there will be some questions, and I give this platform over to Dr. Shantanu Barua for his persuasions. Yeah.
Thank you, sir. May I request Dr. Saurabh Barua, the session co-chairperson, for his comments. Over to Dr. Saurabh Barua.
Yes, Dr. Shantanu Barua, thank you for this opportunity. Indeed, really textbook kind of explanation Professor Sebastiano has made, and we have come to know how seismic hazard assessment map are prepared. In effect, he has raised a very important question, that site effect. The site effect, how it has to be incorporated in seismic hazard assessment map preparation. With an example of Sicily in Italy, he has explained that thing. In effect, if I correctly remember, he has mentioned 1 to 10 hertz in H by V ratio, that resonance frequency was prominent. And that is the most important indication that we have to understand while understanding the site effect. So it's really a wonderful explanation what you have made. I would love to see the research publication in SRL very much, and I request you to send me a copy through this communication. So it's a wonderful lecture. We are enlightened. Thank you. Thank you so much. Nice to see IO as well. Thank you.
May I request our guest, chief guest, Professor A. Eluemi from Obafemi Awolowo University, Nigeria, for his comments. Over to Professor Eluemi.
Thank you very much, Dr. Shantanu. I sincerely appreciate the organizers of this wonderful event. And I give much kudos to our speaker. Though I joined the event as it has been as the lecture has been on, and therefore I sincerely appreciate the part that I happens to listen to. And once again, I want to appreciate my mentor, Dr. Sarah Barua, as well as my chief examiners, Professor J.R. Kaya. and as well as my, my dear brother, Dr. Santonu, for these wonderful lectures that have been organized at the CSR Northeast Institute of Science and Technology. Well, for now, I will not be able to say much because sorry. For now, I will not be able to say much other than to receive much from. Sorry. Okay, thank you so much.
Thank you very much, Ayub, for your heart-touching comments. Thank you very much. Now, may I request Mr. Prasidja for question and answer session. About the Prasidja.
Thank you, Dr. Santanbora, sir. With your permission, sir, I am going to read out the questions. Dr. R. Arun Prasad wants to know, for a region like Malta, I feel the use of distributed acoustic sensing DAS cables are more suitable, which will help in more accurate data and increase earthquake detectability to very smaller earthquake. I want to know the possibility of using DAS cable for these purposes.
I just replied and I put like a little note and comments. I saw the Q&A section. But in general, it's something that I haven't worked on this, so I'm not sure, and I cannot comment on the actual real detectability and increasing in detectability. Maybe it's something that we might want to explore in the near future.
Okay, sir. So the next question is 3 components a single station provide the exact latitude longitude of the earthquake event? If so, what will be the radius for that station that we can locate the event without error?
Now, that's a nice question, and actually it's not the best way that we want to use for the earthquake location. It's just a way and something that the university was implemented earlier just because it was the only method available. The error associated with it is certainly higher than traditional methods. It's quite high, but at least it gives you an indication of the earthquake location. Then it depends on several other factors, and I can place in here in the Q&A section eventually the proper reference to the paper, so eventually you can refer to that. And then always will be available via email and online for any help you might need.
Yes, sir. So the next question is, how much do you think the reliability of single station moment tensor inversion locating using 3 components? Do you need a priori information to constrain the parameters?
Right, no, the moment tensor is not based on single stations. The moment tensor can be eventually done by a pair of stations, but the regular moment tensor that I showed, if you remember, there were like several traces, so it's not based on single station. Obviously, the more, the better.
Yes, sir. So these are the questions from the participants' end, and we have from our end also we have some questions, sir. So do you can like give an insight about if these magnetometers that we are using currently in our station, like we are using proton precision magnetometers. So regarding these magnetometers, we measures the magnetic anomaly. So is there any interpretation that can be done with this magnetic anomaly recorded by a proton precision magnetometer in the seismic hazard management system?
As far as I know, in the conventional seismic hazard approach, magnetometric data, I don't think that will be incorporated, but that's my personal opinion, and I don't think it has been done. I'm not very familiar with the magnetometric data recorded at stations, so I don't think I'm the best person to answer to this question.
Yes, sir. I'm going to over to Dr. Gautam Barua for further questions if he has.
Okay, thank you, Prasija. Good evening, Dr. Sebastiano, sir. I'd like to ask one question regarding seismic hazard assessment actually. As we do hazard assessment, like computing the hazard maps, so we prepare some mesh or grid search pattern. So say it could be of 1 kilometer by 1 kilometer or say 500 meter by 500 meter grid. So is there any thumb rule for ascertaining the grid size, that how big should be the grids? As long as the grids will be smaller, so it will be more precise, but it will take more computational time. So is there any thumb rule to ascertain the grid size, that how big it should be?
This you have to see also with the available data, computational time, and stuff like that. To be honest, I don't really know the exact setting of the problem and the boundary conditions that you're going to set. So I'm not sure. Sometimes even if you increase too much the gridding, you're not gaining any further information. But I should see some data or some examples to be able to reply in a more proper way. But we can have some email exchange if you like. My email address is available, and eventually, if possible, I can try to help.
Okay, thank you, sir.
We have another question here in the box. Sir, what are the minimum station data that you have used for fault line solution?
It depends on several factors, but even with 3-4 stations, it can be a reliable solution. Actually, there is a GRL paper. I don't remember if it was based in somewhere on the Malayan region by Zhu et al., in which they use no, I don't think it's Zhu. I have to look up. I don't remember the authors, but in which they use and they complete reliable moment tensor solution for using just a pair of stations.
Okay, that's all, sir.
Thank you.
Okay, before I have something to comment before you go for next, your next, say, for vote of thanks. There was a question about magnetic anomaly measuring by, by proton piezo magnetometer. How it can help? Yes, how it can help in seismic hazard assessment? Well, it can be, if you use this very high precision magnetometer, if you use this magnetometer for mapping the area, so a detailed gravity map with closed space stations and a detailed magnetic map with closed space station will identify the structure, the fault, or the basement structure, or the dikes. So these detailed magnetic map and gravity map helps to map the subsurface structure, shallow subsurface structure in terms of earthquake source zone. So that is useful, but taking magnetic measurement at a fixed station, I don't think in it any way going to help you to assess seismic hazard assessment. And there was another question, I think Professor Sebastiano has already responded to that, about how many stations required for fault line solutions. I think if you go for classical method with fast motion data, it should be well covered at least Statistically, it should be stable, no less than 20 first person data, no less than 20 stations data. Is 20 first person data. Your network could be of 50 stations. Then only you will get some 30 stations now first person. And if it is digital records, I think Professor Sebastian has already responded to you. There are publications, but I have seen fairly stable solutions can be found by 6 to 10 stations. And single station solution can be also obtained, but not so stable, not so reliable. Over to Shantanu, please.
Thank you very much, sir, for the insight, for a deep insight. Now, may I request Dr. Gautam Burwa for the vote of thanks. Over to Dr. Gautam.
Thank you very much. I am very much privileged on being asked to propose the vote of thanks on this occasion. My sincere sense of gratitude goes to Dr. Sebastiano DAmico, the speaker for today's session, for being with us today and sharing his opinion and findings regarding the side effects and seismic hazard assessment studies. Thank you, sir. We are very much enlightened by your speech. Thanks goes to Professor Chair Kyle, sir, for being with us and sharing the session. You have been always with us throughout the program, sir. Thank you. Thank you very much, Dr. Sorobora, sir, for encouraging us and co-sharing the session and giving your remarks on this topic. Thank you. My sincere thanks goes to Dr. G. Narahari Sastry, Director CSI NIST, for granting the permission and encouraging us throughout the event. Thank you, sir. I would like to thank Dr. Ayodeji. Hello, brother, for being here and gracing the occasion. Thank you. A sincere thanks goes to Dr. Shantanu Barua, convener of this webinar session, for organizing this event and getting us to hear to so much great speeches. Thank you. And my last but not the least, thanks goes to the organizing committee, all of one, and the participants for making this event a successful one. Thank you very much. Good night.
Good night.